Hello, my name is Mike Buller, and this video explores some of the fundamental principles relating to structural analysis and design. Consider a simply supported beam spanning between a pin and a roller. The beam has a cantilever to one end and is subjected to a universally distributed load acting between the supports and a point load acting to the end of the cantilever. A beam is considered statically determinate if the number of unknowns equal the number of equations of equilibrium. If we consider each support, the pin support to the left-hand end has two unknowns. It has a vertical and a horizontal unknown, whereas the roller support has a single vertical unknown. That is, for the beam as a whole, there are three unknowns associated with the supports. If we now consider the equations of equilibrium, you should know from your previous studies that the sum of the moments equal 0. Also, the sum of the vertical actions equals 0. And the sum of the horizontal actions equals 0. That is, we have three equations of equilibrium and three unknowns associated with this particular beam. So we can therefore say the structure is statically determinate. Once we have determined this, we can then go on and draw the free body diagram. Firstly, we draw a horizontal line representing the beam. To that, we add the loads. So firstly, the UD load, and secondly, the point load to the end of the cantilever. We also add the reactions at both supports, so the vertical and horizontal reaction to the pin and the vertical reaction to the roller. And to complete the diagram, we add both the dimensions and the magnitude of the various loads. Once we have completed the free body diagram, we can calculate the vertical and horizontal reactions associated with both supports. If we consider the pin support to be A and the roller support to be B, and we are going to take moments about A to determine the magnitude of the vertical reaction at B. In the calculation of these reactions, we will assume that any action acting vertically upwards is positive. Any horizontal action acting from left to right is positive, and any moment acting clockwise about a point, again, we assume that to be positive. So if we consider the moments at A, we can write the sum of the moments at A equal 0, and everything acting clockwise about A we are going to take as positive. So let's consider the loads one at a time. If we have point A, that is our support, and we have our beam. And right on the end of the beam we have our 20 kilonewton point load acting vertically down. We're going to take moments about A, so this is point A, and we're saying that everything acting in a clockwise direction is positive. So anything acting in a clockwise direction, when I say acting, I mean it's trying to rotate the beam about A in a clockwise direction, that is going to be positive. So for the 20 kilonewton point load, it is rotating the beam in a clockwise direction, so we can say plus 20 times, and if we remember that a moment is a force times its lever arm, So let us take the lever arm as being the perpendicular distance between the load and the point about which we are taking the moment. So in this case it's 10.75 meters. That is your lever arm. So we have 20 times 10.75, and that takes care of the point load. If we now consider the UD load, that is also acting about A. It's a partial load, so it doesn't cover the whole beam, and it is 6 kilonewtons per meter. It also acts clockwise, i.e. it is trying to rotate the beam in a clockwise direction about point A. So we can write it's positive, again, because it's going clockwise, and it is 6 kilonewtons times the distance over which it acts, 8 meters, times its lever arm. And you should know that the lever arm for a UD load is taken from the centroid of the load. So that's where the load acts. The load effectively acts through the centroid. The lever arm is the distance of the centroid to the point about which we are taking the moment. So in this case it's 4 meters, so that's 8 over 2, because the centroid of the rectangle is halfway along. That takes care of the UD load. And the only other action acting on this beam is the vertical upward reaction. We've assumed it's going upwards to start off with, of B, so that's VB. And this one, this time, is acting in an anti-clockwise direction about point A. So we say it is minus, and that is VB times its lever arm, 8 meters. And considering our equations of equilibrium, the sum of the moments at any point equals 0, so therefore all of that equates to 0. And then simplifying this, we can write that 8 VB equals 215 plus 192. Therefore VB equals 50.99 kilonewtons. That is your vertical reaction at B. Now if we consider the sum of the vertical loads equals 0, so again we're considering one of our equations of equilibrium, and this one says the sum of the vertical loads equals 0. Therefore we can write that VA plus VB minus the point load minus the sum of the UD load, all of that equals 0. What we're saying is that the vertical loads going up minus the vertical loads coming down have to equal 0. And then if we add some numbers into this, we get VA as our unknown, that's what we're trying to calculate, plus 50.9 minus the point load, that's 20 kilonewtons, minus the total of the UD load, so that's 6 kilonewtons a meter times 8 meters, the distance over which it acts, that equals 0. And again, if we simplify that, we end up with VA equals 17.1 kilonewtons. So that gives the vertical reaction at A and at B. The last thing to consider is the horizontal actions, and if we scroll back up and just look at our free body diagram, you'll notice that there are no horizontal actions associated with either the point load or the UD load. Because there are no horizontal actions acting, therefore there is not a horizontal reaction at A. So we can say, again, from our equations of equilibrium, the sum of the horizontal actions equals 0. Therefore, HA equals 0. And that's it. That is what we were asked to solve initially. We have calculated the vertical reactions associated with a simply supported statically determinate beam. I hope you have found this video useful. If you have any comments or suggestions, please do send me an email at the address shown on screen. Thank you for watching.